So, thermodynamics is a scientific discipline concerned with the relationships among heat, temperature, work, and energy. It explores the principles governing the transformation of energy between different locations and forms. Scopes of thermodynamics studies the key properties such as pressure, volume, temperature, internal energy, enthalpy, and entropy. It also explains various processes including isothermal, adiabatic, isobaric, and isobaric. The four fundamental laws govern this field. So first, the zeroth law defines temperature at thermal equilibrium. The first law states energy conservation. Second law introduces entropy and the natural direction of the processes. The third law describes system behavior near absolute zero. The field scope spans multiple disciplines, from mechanical engineering, chemistry, to biology, and environmental science. The journey of thermodynamics began in the 17th century. In 1650, Otto von der Rey invented the vacuum pump, sparkling experimental studies on air pressure. In 1662, Robert Boyle discovered the inverse relationship between pressure and volume of gases, now known as Boyle's law. Fast forward to the early 19th century, Sadi Carnot laid the foundation for thermodynamic cycles, introducing the ideal heat engine concept. Around the same time, James Prescott Joule confirmed the equivalence of mechanical work and heat, leading to the first law of thermodynamics. Rudolf Clausius and William Thomson, also known as Lord Kelvin, formalized key principles and introduced entropy, establishing the second law. Walter Nernst later developed third law, describing entropy at absolute zero. So by the late of 19th and early 20th centuries, Ludwig Boltzmann and Josiah Willett-Curves connected thermodynamics with atomic theory, giving rise to statistical mechanics, linking microscopic particle behavior with macroscopic properties. A common misconception is that temperature directly measures the average kinetic energy of particles. However, temperature primarily reflects thermal energy related to potential energy, especially electron orbital energy, rather than just kinetic energy. So this misunderstanding arises from an incomplete grasp of Brownian motion and the components of internal energy.
Alright, thermodynamics can be studied in two main ways. The first is classical thermodynamics, which looks at the overall system without needing to know what each molecule is doing. For example, we can measure gas pressure with a gauge. The second one is statistical thermodynamics, which focuses on the average behavior of billions of tiny particles to explain how things work.
Thermodynamics can be understood from two different perspectives, the macroscopic and the microscopic view. The macroscopic view looks at a system as a whole. It focuses on measurable quantities like temperature, pressure, and volume, without considering the behavior of individual particles. For example, when we say water boils at 100 degrees Celsius, that's a macroscopic observation. On the other hand, the microscopic view, also known as statistical thermodynamics, looks deeper into what's happening at the particle level. It explains thermodynamic properties based on the motion and interaction of atoms and molecules. For example, temperature in the microscopic view is related to the average kinetic energy of the particles.
There are three different terms that is important. So the first one, system. System is defined as the body of a matter that is separate from its surrounding. And then, surrounding. Surrounding is a region that is outside of the system. Next is the boundary. Boundary is a real or imaginary surface that is separate the system from its surrounding. So open system is basically a system that has external interaction. Such interaction can take the form of information, energy, or maybe material transfers into and out of the system. Next is closed system. So closed system is a natural physical system that does not allow the transfer of matter in or out of the system, while the transfer of energy is still allowed. So for the last system, isolated system, which is the system that enclosed by a rigid, immovable wall through which neither mass nor energy can pass.
A thermodynamic property is any measurable quantity that describes the state of a system. So these properties are important because they have a few key characteristics. First, they have a definite value when the system is in a specific state. Second, they are independent of the path taken to reach this state. Instead, they depend only on the current condition of the system. That's why we call them as state functions or point functions, because they are based on the state, not how the system got there. They also can be expressed as exact differentials, which depending only on initial and final states. Thermodynamic properties are divided into two types. First, intensive properties like pressure and temperature, which independent of the size of the system. Second is extensive properties like mass and volume, which do depend on the system size. At 12,000 meters outside, the pressure is only 20 kilopascal, which is too low for humans. Aircraft cabins stay safe using a pressurization system. Engine blade air is compressed, cooled, then expanded before entering the cabin. Inside, pressure is 75 kilopascal and temperature is 23 Celsius, are kept comfortable, while mass flow and energy help engineers monitor system performance.
In thermodynamics, the state of a system is its condition described by properties like temperature, pressure, volume, enthalpy, and entropy. Some of these properties, like temperature and pressure, are intensive. They do not depend on the amount of substance present. Others, like volume and energy, are extensive, meaning they scale with the size of the system. A system is in a fixed state when all of these properties are known and remain stable over time. On the other hand, equilibrium is reached when all parts of the system are balanced. There is no heat flow in or out, pressure is uniform, without any unbalanced forces, no ongoing reactions, and all phases are stable. For example, if you leave a hot cup of tea on the table, over time its temperature will decrease until it matches the room temperature. This is a system reaching new thermal equilibrium.
Hi, my name is Nunadira Haitani and I'm going to present about the zeroth law. Although the name is zeroth law, it was founded after the other law, which is the first, second, and the third law of thermodynamics were founded. However, instead of naming it as the fourth law, it was named as the zeroth law by the British mathematician Ralph H. Fowler because how the law are fundamental compared to the other. The zeroth law states that if two thermodynamic systems are each in thermal equilibrium with a third, then they are in thermal equilibrium with each other. This can be simply explained where if A is in equilibrium with B, and A is also equilibrium with C, then B and C are in equilibrium too. Therefore, A will equal to B and equal to C. This law is fundamentally applied in thermometers. When we put the thermometer in a hollow body and the heat flows until the thermal equilibrium is reached, the mercury expands and rises in the tube, reading its own temperature. Another example is that the measured temperature in the room is 26 degrees Celsius. With zeroth law, we can assume that all the things in the rooms have the same temperature. The zeroth law of thermodynamics may look easy and simpler compared to the other law, but it is one of the most essential principles in science. It defines the thermal equilibrium and allows the opportunity to measure the temperature in an accurate way.
Hello everyone, my name is Muhammad Rafiq bin Abdul Basit, and today I will explain the first law of thermodynamics. So this law, also called the law of energy conservation, states that energy cannot be created or destroyed, only transferred or transformed. So in thermodynamics, we write it as delta U equal to Q minus W. Delta U is the change in internal energy, Q is the heat added to the system, and W is the work done by the system. So if we heat a gas or do work on it, the internal energy increases. This explains how energy moves through system, like how sunlight become a chemical energy in plant and the kinetic energy when we move. However, this law doesn't tell us whether a process is spontaneous or what direction heat flow.
The second law of thermodynamics states that in any natural process, the total entropy or disorder of an isolated system always increases over time. In simple words, energy tends to spread out and become less useful for doing work. This is why, for example, heat naturally flows from hotter to colder region, and not the other way around. It also explains why a machine can be 100% efficient because some energy is lost to the surrounding as heat. This law reveals the error of time, showing us that systems naturally move from order to disorder.
Now we are going to move on to the applications of thermodynamics in daily life. First, your fridge uses the second law of thermodynamics, reversing natural heat flow.